You hit it?
Yes.
Oh, how long have I been on tape?
Oh, 4 seconds.
Okay, phew. All right, just checking, because otherwise we'd start again, because I don't enjoy editing. So I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students, for the weekend that's about to start. Help us to use this time wisely, Lord, and just understand what we can about variational calculus in the time that we have, Lord. In your name I pray. Amen. So guys, I told you what I can about theory of extreme values and Lagrange multipliers. I hope you got something out of those. If you have further questions, I'm happy to talk about it. So one thing I would tell you is one of the problems I assigned you in the homework was to calculate the extreme values of a quadratic form on the n sphere. I actually worked that out last cycle of this class. So if you get stuck on the calculation, if you look back at the videos from 2 years ago, I work it out in gory detail. It takes me about a half hour. Not that it should, but it's just step-by-step calculation. I actually have to get into components and such. The formula for a quadratic form would be something like the sum I comma j, x sub I, a sub I j, x sub j. So you can partial differentiate that with respect to the ith coordinate and actually work out the gradient explicitly, but you should use an index notation. And I actually go through the details of that. It's neat because we derive that the extremal values for the quadratic form on the sphere are met exactly by eigenvectors. So we derive the necessity of eigenvectors from Lagrange multipliers. It's these really interesting homework problems. Make sure you do that one. It's so much fun, and I wanted to make sure that you're not alone in doing it. So I actually did it. The point is not to go watch the video and copy the solution down. Try for yourself. You probably can do it without watching my video anyway. Okay, there's that. So any questions about extreme values or any of that? That's okay. Okay, with that then, I'm gonna talk about variational calculus. So have you guys ever heard of variational calculus? Probably not. So here's some questions that are contained in variational calculus. Here's some typical questions that are answered by variational calculus. And these are old questions. In fact, variational calculus was part of the mainstream of the calculus education up until, I don't know, 100 years ago or something. You used to find this in the standard books. But at some point, it became its own course. And then we stopped teaching it to undergraduate math majors. Sad. But anyway, number one, what's the shortest path between 2 points on a surface? Number two, what is the path of least time for a mass sliding without friction down some path between 2 given points? Question 3, what's the path which minimizes energy for some physical system? Here's another question. Given 2 points on the x-axis and a particular area, what curve has the longest perimeter that bounds the area between those points in the x-axis? So if you look at all these questions, the answer to these questions is a what? It's a path, right? Or the answer might be a surface. I mean, the answer to these questions is something, basically these questions make us think about the variable in the calculus being a path. And that's something new, see, because that's an infinite dimensional thing. Our variables are usually real valued variables, right? Not function valued variables. So basically, we just talk about the basic setup here. What I'm going to do for you right now is I'm going to derive the so-called Euler Lagrange equations. All right. So derivation. And so the story goes something like this. Euler was able to solve these sorts of problems by taking the path, the hypothetical path, which would be solution, and like just thinking about points along the path, right? Like replacing the path with some sort of polygonal approximation. So you have this finite set of points, and then use the coordinates of those points as the variables for the problem, convert it to some sort of monstrous maximization problem of many, many variables, and somehow from all of that he derived these Euler Lagrange equations. Now, that's fantastically complicated. Lagrange came along and he adopted more the viewpoint I was just espousing, which is that the variable is a function and you can differentiate a function of functions in a systematic way through something called the variation, which is what I'll be trying to explain to you right now. And so Lagrange greatly, vastly improved Euler's view. So here we go. What we have to do is we have to consider some space of functions, all right, some potential solutions to our problem. And we're going to say that F naught is the space of admissible solutions. So this is some sort of set of functions, all right? That's a set of functions. And usually you assume this admissible space of admissible solutions, it has some kind of property that you're assuming. So for us, for the sake of discussion, we're going to assume all the functions in F naught have graphs which include x1, y1, and x2, y2. All right? And then we're going to consider a functional, right? J. J is going to be a functional. So J is going to map F naught to F naught again. And this functional, we're going to let be defined in terms of the integral of some function f, which we're going to call a Lagrangian, in honor of Lagrange, of course. So J of y, square brackets, because y is a function, x1 to x2, integral from x1 to x2, f of y, y prime, and x. So we're going to assume that this Lagrangian depends on the function, its derivative, and possibly its independent variable. All right. So here we suppose that f is given, but y is a variable. All right. F is given, but y is a variable. And so suppose we're given a function y star, which is in F naught. All right. So consider, suppose you have y star, an element of the space of admissible solutions, right? Then you could create another thing in the space of admissible solutions if you have another function, eta, such that eta of x1 equals to eta of x2 equals to 0. So if I have this eta, another function, all right, that is 0 at the endpoints, then it's fairly clear that if we look at y equal to y star plus alpha eta, then this y is another thing in F naught. Do you see why? It's helpful to draw a picture. So here's my point x1, y1. Here's my point x2, y2, all right? The graph of, y star is whatever it is, like that maybe. So perhaps y, maybe this could be, here's y star plus eta, perhaps, that would be alpha equals to 1. Or maybe down here is not, sorry, I can't do, I tried. It's probably not a very good graph, but maybe that's alpha equals -1. Okay? So when you have alpha equals to 0, as you vary, alpha is here a real number, okay? And so if we pick different real numbers, we're kind of just blowing up this eta, right, above or below. And maybe eta doesn't have to stay on one side or the other. Eta could cross the graph as well. So the real story is much more complicated, right? Eta could like cross y star. And the point is, as we adjust alpha, that variation, see, eta is the variation, right? That's kind of the idea, is that by adjusting this alpha, we're taking paths which are close to y star, but not exactly y star, right? By adjusting this alpha, we've got paths which are close to y star, but not quite y star. Okay, so the notation, to be more precise here, is that y of x comma alpha is equal to y of x comma 0 plus alpha eta of x. There's the dependence. So here we're supposing that y of x comma 0 is that y star that I picked at the beginning, okay? So far so good? Do you guys understand the setup? Is there something I have left out? Alpha is a real variable. What's that? Eta, yeah, eta has to be an element of F0, yeah. Well, does it? No, I don't think it does. I mean, it has to have eta of x1 is 0, eta of x2 is 0. So no, it's not in there, no. But this y of x comma alpha is in there for any choice of alpha, because we're considering eta to be vanishing at the endpoints. So anyway, to emphasize here, so we have x maps to y of x comma alpha gives a function, right? Gives a function in our F naught. So the variation definition, we write delta of y equal to alpha eta of x. So with this notation, essentially at this point it's just notation, we have y of x comma alpha equal to y of x comma 0 plus delta y, right? So we take our given path in the space of admissible solutions, and we consider a variation about that path, right? So, and then the logic here is very, very much akin to that we use in the Lagrange multiplier method, right? What's the Lagrange multiplier method start with? The assumption that there's an answer out there to find. Same thing here. Suppose that this, suppose that this Lagrangian, this functional, what we want to do is we want to suppose there exists an extreme value, all right, an extreme path for this functional, right? So suppose, well, before I do that, notice that j is now a function of alpha, right? And we can write it as the integral from x1 to x2 of what? Of f of y of x alpha, y prime of x alpha, and x dx. Yeah. So here's the thought process here is, suppose then that y star of x is actually an extremum of the functional, right? if y star is extrema of j, then surely we should have what? We should have partial j, partial alpha, right? And y star is what? In this, y star is again, y star of x is again y of x comma 0, right? So in this family of paths, right, it's reached when alpha is equal to 0, right? So what should we be able to say about the partial derivative of j with respect to alpha? Alpha is a real variable. I can calculate partial derivatives of it, right? As we vary alpha, we're sorting through different variations for a fixed eta, right? For a fixed eta, we're adjusting alpha, sorting through different variations of the extremal solution. It must be, this has what? At alpha equals to 0, we get what? 0, right? It should be a critical point. To draw the picture sort of abstractly, it's something like this. F naught, right? Space of all functions. Here's my extremal point, y star, right? And then there's a path through here. Maybe I'll call it W sub eta, right? When alpha, this is things in here. This contains in it y of x comma alpha. I don't want to write that x there. Y of blank comma alpha. Those things, right? Those functions. As alpha varies, we go along this subspace of function space, the W alpha, W eta. But if this is an extreme value of the functional, right, then it must be that this real partial derivative is 0, because if it's an extrema for all possible directions in the function space, it must be an extremal for this particular restriction to this particular path in function space. This is the same logic we use with Lagrange multipliers, but there was a finite dimensional context, right? Okay, so then the Euler Lagrange equations are simply nothing more than putting this into practice in the lens of partial differentiation in the chain rule for the Lagrangian. Okay? So let's calculate what would partial j, partial alpha would be, partial alpha of the integral from x1 to x2 of f of y of x, so much writing. I'm going to get tired of writing very soon. Sorry. Y of x, good grief, x. So the first move, and if you'll allow me to save myself some writing, we're going to assume, and this is one of the things that I admittedly have left out of this offering of, we're missing a Travis. Oh. Oh no. I hope he's sick. Wait a minute, no. That seems wrong. And yet I do. No, that's wrong. I shouldn't hope he's sick. I really hope he hasn't dropped, because, I mean, we need representation from the... He's busy. Okay. Doing important things. Something's more important than this? No, sorry. No, but one of the things I often cover in here, besides the things I'm covering with you guys, is differentiating under an integral. All right? I cut that out this semester because I wanted to cover more of that book. My apologies. But one of the things that we can learn there, and in my defense, I think it really belongs in real analysis anyway, but is that for a function which is nice enough, we can bring the partial derivative inside. Now that's assuming some sort of uniform condition on the f. But that condition will be met for the examples we're interested in, so it's okay.
Is that the kind of technique that people talked about Feynman using?
Yes. Yeah. But this predates Feynman by a couple centuries. But yeah. So then we differentiate this with respect to alpha, and then that's the chain rule. So we've got partial f, partial y, partial alpha, plus partial f, partial y prime, partial alpha, plus partial f, partial x, partial alpha, dx. Now, does the variation have anything to do with x at all? For our problem, certainly not. So this piece is kaput. It's gone. There's no alpha dependence. X has no alpha dependence. On the other hand, we have y of x alpha equals to, what was it? Y star, right? Y star plus alpha eta. So if I differentiate this, it's just, stupid notation, y star prime plus alpha eta prime, right? Again, there's no x dependence here. So if you look at this, we can see partial y x alpha prime partial alpha is just what? This has got no alpha dependence, right? And so it's just gives me eta prime. So this is eta prime. What's partial y partial alpha? Right, partial y, partial alpha, this y is just eta. Thank you. So this is eta. And so we've got integral from x1 to x2, partial f, partial y eta, plus partial f, partial y prime, eta prime, dx. Now, how do you convert an eta prime to an eta under a derivative, under an integral like this? Like how can I move this derivative from this symbol over to that symbol? What technique does that? How about this? You guys check this out. What if I take d dx, right, of partial f, partial y prime, eta? What's that give me? Product rule, right? d eta dx is I'm using eta prime for that, right? So look at this. We have this term already. So by the product rule, I can trade that for right? This is integration by parts, by the way, that I'm doing. Integration by parts allows you to move derivatives from one term to another, provided that the piece that's like the UV piece vanishes, right? So why would this, see, this is, we're integrating this thing from x1 to x2, right? What happens to this term under this integration? We hit something times eta of x1, something times eta of x2 minus partial f partial y prime at x1, eta of x1. But eta of x1 and eta of x2 are, by assumption, 0. So this term is no more after applying fundamental theorem of calculus. And then you've got this guy and this guy, right? And you can factor out the eta. See, we got x2, x1 to x2, partial f, partial y, minus d dx of partial f, partial y prime, eta dx. Now this has to be equal to 0. But for which eta does it have to be equal to 0? What's that? Eta could be 0. Sure, it's a good math major answer. Very good math major answer. Eta could be 0, right? But the point is, if that's going to be an extremum, right, this should be true for arbitrary etas. So, in other words, maybe there's W sigma, where that is typically got y of, x comma sigma. Y of x, where I don't have no notation for it. Typical thing in here would be y star, plus alpha sigma, where sigma of x1 equal to sigma of x2 equal to 0. Or maybe I should call it eta tilde or something. The point is, I could take arbitrary variations built from different choices of eta, and all of those must return this condition that partial j partial alpha is 0 if it's going to be an extrema. So think about that. That means that this integral has to be 0 for arbitrary functions here, which vanish at the endpoint. What does that force this integrand to be? Yeah, it forces it to be 0 at the extremal function. In other words, we've derived the Euler Lagrange equations. The Euler Lagrange equations simply state that we need to solve, and I've already forgotten them. Oh, for shame. Partial f, partial y, minus d dx, partial f, partial y prime, equals to 0. The solution to this set of differential equations will give us the extremal points of that functional. But you see the technique we use to derive it, it's really just like what we've already been doing, right? Granted, there's a lot of analysis that we're not really dealing. That was some very sneaky stuff I just did there, right? This is an infinite dimensional context. I'm arguing that this theory of optimization we've studied in finite dimensions can be extended to infinite dimensions, and that is not something I've really earned the right to say in here. Right. Now, let me show you how I saw these things derived for me as a physics undergraduate. I wanted to make sure I wrote this out, because I think if you don't see me write this out, you won't understand it. The rest of what I'm showing you today, it doesn't matter if you see me write out for the most part. I will write some more out, but a lot of it I just need to show you. If I can find my laser. Man, I wish Travis was here. I think this is one of the more important things for him to see. Oh well. There it is. Come on. Come on. You can do it. So, in physics, what they'll do is they just introduce so here's what I just went through with you guys, page 115, all right? Here's what it looks like in physics, at least the undergraduate physics I had. Here would be the corresponding, let me just turn off the front ones. Come on, come on, submit. There we go. So they just take the variation of the functional. They say you take the delta of it. And the way that, so you take delta of j, where j is the same thing I had, and then you take delta of this, but since f is nice enough, you can pass the delta inside the integral. But then the variation of f satisfies this chain rule. So it's like partial f, partial y, delta y, partial f, partial y prime, delta of y prime, partial f, partial x dx. Now, it's easy enough to see that that goes to 0 because our variation is 0 at the endpoints, right? Fine. And then through some manner of magic, they say, oh, well, the variation of dy dx is the derivative of the variation. And then, that just angered me as an undergraduate double major in math and physics. I was just like, what is that step? All right. This thing I just did over here is to explain that step. Okay? It's somewhere in there. And once you get to that, then we integrate by parts, and we're right back where we got to. Now, there's nothing wrong with, I'm not criticizing my professors. Like, this is the right way to have taught physics undergraduates because it focuses on the calculation which is important to physics, right? This substructure, this mathematical substructure, it's not that important to physicists, right? So, okay, let's go on here. Let me show you some examples then. I mean, we want to do more than just talk about the derivation of the Euler Lagrange equations. We want to see some examples. Now, I'll probably make this one of your homework questions because I know this is a hang up for me. If I try to derive it right now, I won't be able to do it, but it's simple. I've done it in the past. I know it's not that hard. It is super nice to prove that the Euler Lagrange equations can be rewritten like this for our functional. This form of the Euler Lagrange equations is much nicer for examples sometimes. So you can rewrite the Euler Lagrange equation like this somehow. It's like a product rule rewriting or something like that, okay? It might involve the chain rule. So let's look at our first example. Suppose you want to minimize the distance between 2 points in the plane, right? What's your functional? It's the arc length functional, right? The square root of 1 plus y prime squared dx, this calculates the arc length of the graph between x1 and x2, right? So the Lagrangian here is the square root of 1 plus y prime squared. So what's partial f, partial y? Well, no y dependence, so that's 0. What's partial f, partial y prime? Well, it's y prime over that root. The Euler Lagrange equations, here they are. What do they say? They says that d dx of this monstrosity is equal to 0, right? But that's nice because that means that this must be a constant, right? And then you square both sides, and you can solve for y prime. Y prime squared is this constant, which then means that dy dx is plus or minus just square root of that constant. Call it m. Integrate both sides. You got y equals 2. Right, mx plus c. So and then of course you have to choose the m and the c to fit the 2 points, the x1 and x2, right? So this is the derivation that the shortest distance between 2 points in the plane is a line. I can do this without variational calculus also, right? Yeah. We can all do this with like inner products and such. There it is though. This one maybe not. Suppose you want to look at the surface of revolution formed by some curve, right? So you take some curve, you rotate it around the x-axis, it gives you a surface of revolution. Then you can ask, for between two given points, you try to find the surface of minimal surface area. So the surface area is given by this integral from x1 to x2, 2 pi y. So this is the standard surface area of a graph formula. But we can look at this as problem of variational calculus. I mean, the Lagrangian is exactly this, right? And so this one's more interesting because now we have both a y and a y prime dependence in the Lagrangian. See, partial f partial y is 2 pi times that root. But partial f partial y prime is this thing. There's the division, right? Something that's bothering you right now, right, is that I'm saying that y and y prime are independent variables, right? As math majors, this troubles you a little bit because you're like, but it's the derivative of y, so those are independent. Those seem very dependent, right? Some similar abuse is done in complex variables where we say z and z bar are independent variables. But like, what does that mean? Because z conjugate is to z's conjugates to z. That's a dependence. What? That one's harder for me to explain. This is really just a notation. I mean, the truth be told, we're taking the problem that's given and we're lifting it to what's called the jet bundle. The jet bundle is this space where y and where the velocity and the position are independent variables. You're doing the calculation up there and then you're projecting back down to reality. So you're working in a context where y and y prime are independent. We do this in differential equations all the time when we do reduction of order. We introduce these variables that are for the velocity, the acceleration, so forth and so on. That is essentially working on the jet. That's what that technique is. Its formalization is called the jet bundle. But anyway, let's not talk about fiber bundles. Let me behave. So, your homework problem. Recast Euler Lagrange equations as this. Yay. So, applying that to this problem, that gives me that the derivative of all of this is 0. So you see why you want the problem, because then you don't have to work, at least at the first stage in solving. You just get, well, that's equal to a constant, and then you can go from there. Listen, the techniques to solve these equations, solving Euler Lagrange equations is a multifaceted and varied problem. I will not teach you in here how to solve them. I mean, I will ask you to solve a few, probably. The actual, how do you solve them? There's so many different ways. I mean, typically you look to find everything, there's strategies, right? If you find the derivative of everything is equal to 0, you get to say that everything is a constant, right? But that constant actually involves derivatives, so then you can integrate again. It's some sort of like looking for constants and integrating. This is kind of our ninja way. Anyway, so that's got to be a constant. Make a common denominator. It gives you that this has to be a constant, and then you get this, all right? And we're getting closer to a differential equation. Take the square root, both sides. And so we get that. Now, notice that I separate variables. I get dx is k dy over the square root of y squared minus k squared. I don't know why we don't have an undergraduate class in this. Can you see why? But integral dx k dy over this, but that's inverse hyperbolic cosh, woohoo, of y over k, and there you go, y equals k cosh x minus c over k. This is called a what? What's the surface of revolution? If you take a hyperbolic graph and rotate it around, what kind of surface is this called? Hyperboloid. Yeah, I don't know. I was actually asking you guys. They're called catenoids. So this is a catenoid. A catenoid is the surface of minimal surface area formed by a surface of revolution. And nature is lazy, and many things we observe in nature are extremal. They maximize or minimize some functional. In this case, surface area. So soap bubbles are catenoids for this reason. It minimizes the energy that's needed for the bubble to exist. That's what it actually is. It's always about minimizing energy. In the interest of getting to that, let me go on. Another classic problem is the brachistochrone. Do you think I spelled it wrong? I think you're probably right, but whatever. So sorry. You get what you pay for, right? So the question is, you got a particle, it slides freely along some curve between 2 points, all right? And the question is, it slides freely along these 2 curves under the influence of gravity, where we take y to be the vertical direction. Which is the curve of quickest descent? So, you know, if the points are like this, we don't need variational calculus to answer the question, right? The path of quickest descent is clear, right? But what makes it interesting is when x1 and x2 are not the same x, right? So when you got, like, you know, it's over here, then the question is, like, is this the quickest path? Or what about this one? Or what about this one? Or what about this one? I mean, you got lots of choices. Some start out fast and end slow. Some start slow, end fast. And you got all kinds of variations in between there. I mean, what's the answer? What's the path, given that the particle slides freely, of quickest descent? So what you're trying to minimize there is time.
The time from beginning from start to finish.
Right. So you want...
Like, what is the maximal velocity reached?
No. We want to minimize time. So what we need to do then is to, well, it's, first of all, energy is conserved since it's sliding freely. So we have that 1/2 mv squared is mg y minus y1, where y is like a point in the middle. And, sorry. V is this, but v, of course, is also what? It's the speed. It's ds dt, right? So since v is ds dt, you can solve for dt. dt is ds over that. But remember, ds is also this 1 plus y prime squared dx, right? The arc length in terms of a graph is the square root of 1 plus y prime squared times dx. This is ds for a graph. ds for a graph is this guy. And that down there is the v. So there you go. This is your functional. That's your Lagrangian this time. This is the Lagrangian. Euler Lagrange equations will tell you how to find the path of quickest descent. This one hurts a little. So yeah, these are the Euler Lagrange equations. I mean, even the partial derivatives are kind of drag here. Here's partial f, partial y prime. Partial f, partial x is whatever. I forgot what it is. Oh, it's 0. Oh, that's not too bad. So basically, we've got the thing in brackets has to be a constant, right? So we get that this minus that is a constant. I label the constant that because that's what was shown to me in physics. So I know it works out nice if you do that. And it follows this, then this, then this. They solve for dy dx. You get that. You tilt your head and squint, relabel constants. You get that x is equal to plus or minus that. Hooray. And then that's got these solutions, like so. That's the solutions to that differential equation. By the way, I'm following Arfken, which is a nice mathematical physics book. Mathematical Methods for Physicists book, actually. Anyway, this is a so-called what? Cycloid. So a cycloid, it turns out, the curve you get from like rolling a quarter along a surface, that part of a cycloid gives you the curve of quickest descent. This is a problem you could not solve with your previous methods, right? Our multivariate calculus course can't touch this problem. It's outside its scope, right? Because your solution, you have to think about different possible functions being answers, right? So this is a problem of variational calculus. It's not a new thing either. These problems were studied by Newton. Galileo tried to solve this problem. He thought the answer was a parabola, I think, if I remember right. Anyway, any questions? Yeah. Actually, don't ask me questions just yet. This one's really just a difficult problem. That's all there is to it. There is Euler Lagrange. You know, you can have a functional with more variables. You could have not just one dependent variable, but you could have several dependent variables, say n of them, and then you could have time. And then the Euler Lagrange, you get a set of Euler Lagrange equations. You get an Euler Lagrange. you get an Euler Lagrange equation for each y sub I. So if you've got like 3 dependent variables, you get 3 Euler Lagrange equations, 1 for each. Maybe your y1, y2, y3 is like x, y, z being position. So you get Euler Lagrange equation for x, you get Euler Lagrange equation for y, you get Euler Lagrange equation for z. The derivation is the same, pretty much. So it's kind of boring in the sense that if you've got a bunch of variables, then you get n Euler Lagrange equations, 1 for each variable. Okay. I agree. It's pretty awesome, right? This stuff gets much more interesting when we talk about physics. Okay. So in physics, we can talk about the kinetic energy, right? Kinetic energy of a mass is 1/2 mv squared. But mv squared is what? It's m x prime squared plus y prime squared plus z prime squared. But being good physics students, we'll use x dot, y dot, z dot. Also because it gives you much more joy to write x dot squared as opposed to x prime squared. Do you see why you prefer the dot notation? Yeah, it's way better for these kind of formulas. So for a free particle, that's it. The total energy is just kinetic energy. And so this is called the action for the particle. The Lagrangian is just this. And so, I mean, the kinetic energy is the Lagrangian in this case. And so partial k partial x is dt and like this and like that. These are the Euler Lagrange equations. What do these give you? Well, that's 0, that's 0, that's 0. What's partial k partial x dot? You get m over 2 times, excuse me, 2x dot, x what? Oh, I'm sorry, I'm differentiating partial x dot, right? So it's just mx dot, right? So this is just mx dot, that's just my dot, that's just mz dot. Check it out. 0 is mx double dot. 0 is my double dot. 0 is mz double. So yeah. So if you've got a particle with no force applied, its equations of motion are that mass times acceleration 0. This is how the Euler Lagrange equations reproduce these things, right? And so that straight line motion is the path which minimizes energy. Usually that would be something, we state Newton's law, right? We could write down the energy function and we can prove the energy is minimized by that path or something relative to some other path. Here we're starting with energy being minimized as our foundational principle. From that, Euler Lagrange comes and then we solve. So of course solutions automatically minimize energy. That's the starting point of the Lagrange equation, is that energy is minimized. So this is Hamilton's principle. States that there's this quantity S, which is called the action. And Hamilton's principle states that the laws of physics all arise from minimizing the action of a physical phenomena. All right. Let's see here. I think I have. You can also find geodesics, right? I mean, I showed you one of these. This is kind of stupid, right? The geodesic of point on the plane, right? Let me put this away for a second. Oh, I was about to ask you guys to hit the lights, but it's on me, isn't it? Yeah. Here, let's look at this problem. So, example. Suppose you're looking at a cylinder, right? And maybe this is x squared plus y squared equals to r squared, right? So I can take 2 points, right? Say All right, at this point, it becomes much easier if we don't insist on using Cartesian variables, but instead think about this in terms of, say, cylindrical variables. So of course, this is just what? This is really just r equals to r, right? And so if you don't mind, I'm gonna let x equal to. I'm gonna use an s, and well, fine. No, what? No, I can't do it, guys. S. I got to do s here. X is equal to s cosine theta. Y is equal to s sine theta. I'm going back to my roots. Physics, we use this. Z equals to, in fact, well, I'm going to shut up. Well, Z is Z. Fine. All right. So what happens if we calculate x dot squared plus y dot squared plus z dot squared? There's various ways of deriving this, but I'll do the lowest tech one for you guys for the moment. What happens if we're assuming that s and theta are functions of time? I may have done this for you in Calc 3, Sam. Sorry. Sam, of course. And so that would be s dot cosine theta minus theta dot s sine theta squared plus s dot sine theta plus s cosine theta, theta dot squared plus z dot squared, yeah? So if you look at this, the cross terms cancel, and you're just left with s dot squared plus s squared theta dot squared plus z dot squared. So that's the, what that is this is really the formula for, now my S is caught up to, now I'm in trouble. Because I want to say that, well, I mean, this is v squared, right? This is the speed squared in cylindrical coordinates. And I want to say that that's the infinitesimal change in arc length with respect to time squared as well. But then that's where I'm getting into trouble. So let's use this. Ha-ha. See? Ha-ha-ha. There we go. Right? So, yeah. So what happened? So on the cylinder, on cylinder, we have that s dot equal to 0, right? So if we impose that constraint, the thing we want to look at, S, which is got, theta and z, right? It's got theta and z. It's going to be something like integral over appropriate times, let's say. I don't care what time. Now, I say that instead of, these square roots are just silly. Like, who needs square roots? Let's minimize the arc length squared, That makes life easier. So our thing we're going to, sorry, I'm losing my ability to speak. S squared theta dot squared plus z dot squared dt. But that s squared is actually what? I guess I should write r squared, huh? Okay, so what are the Euler Lagrange equations for this functional then? So, oh yeah, thank you. So if I think of this thing as being my Lagrangian, right? then partial L, I want partial L partial theta to be d dt of partial L partial theta dot. You know, and I want partial L partial z to be d dt of partial L partial z dot. There's a better way to do this example, but I'm too far in. I'm too far in. So what is partial L partial theta? Zero, very good. Partial L partial theta dot. What did you say? 2 r squared theta dot. All right. Very good. And this one? Z dependence? Nope. Z dot dependence? Yep. So d dt looks like 2z dot, yeah? So what do we need? We need, oh, this is pretty simple actually, right? So what we really have is that theta double dot is 0 and z double dot is equal to 0, right? You can solve these all day long, right? Theta is equal to theta naught plus theta 1t, and z is equal to, you know, z naught plus z1t, right? And so if we look at a path, r of t, which is equal to, you know, r cosine theta, r sine theta, z, what we got? Man, I have ruined this example, guys. I'm sorry. I mean, this is in fact the answer, but it's just not at all. Like, the way to do this problem, to make it like cool, is to use theta as a parameter, I think. I'm trying to remember. Dang it. I guess I need to admit defeat and go back to my notes. This is easy enough. I can tell you what that path is. It's easy enough to illustrate, you know? Oh, well, fine. So, like, here's 2 points. 2 points on the cylinder, right? What's the shortest path between those points? It's the line that you can draw on the cylinder when it's not, you know, curved. That line is the geodesic. This actually derives it, although it may not be transparently clear to you. I mean, this is that path. It's a line in the z theta space, and that gives you the geodesic up here like that. Yeah. Okay, so this is an open question for me, Kang. Like, I know I must be missing something by not taking the square root, but I don't have a good counterexample to how that gets me into trouble. Because it seems to, go back to optimization in calculus 1. Find the closest point on a line to a point off the line. You got a choice. You could minimize the distance, or you could minimize the distance squared. Which should you minimize?